Welcome to the Explainer. Today we're doing something really fun. We're going to take a peek right under the hood of modern AI to look at the actual math, specifically the vector math of query and key matrices. We're going to completely demystify exactly how these models mathematically decide what to focus on when they're processing text.
So here's our roadmap for today. 1. The AI pronoun problem. 2. Queries, keys, and values. 3. The math of scoring keys. 4. Scaling and softmax probabilities. And finally, 5. Multi-head attention perspectives.
All right, let's jump right into section 1. The AI pronoun problem, a linguistic puzzle.
Okay, I want you to consider this sentence. The trophy didn't fit in the suitcase because it was too big. Now, as humans, we just instinctively know that it refers to the trophy, right? We have that implicit world knowledge. But think about it. How on earth does a machine figure out that contextual link using nothing but math?
Well, legacy models used to read text completely sequentially, literally one word at a time. And because of that, they suffered from what was basically a fading memory bottleneck. By the time the AI reached the end of a long sentence, its memory of the beginning was already totally diluted. But self-attention? It completely shatters that limitation. Instead of a sequential line, it creates a fully connected mathematical web where every single word looks at every other word simultaneously.
Which brings us to section 2, queries, keys, and values, the library analogy.
To really wrap our heads around this, imagine walking up to a library counter with a very specific question in mind. In our AI model, this is the query vector. It represents exactly what a specific word or token is searching for. So our word, it, basically generates a query card asking, hey, what noun am I mathematically supposed to be replacing here?
Now, look behind the counter. Every single book has a descriptive label on its spine. These are our key vectors. Basically, every surrounding word is broadcasting a key that announces its semantic identity and its role in the sentence. They're all just sitting there waiting to be checked against your query.
And finally, we have the value. If the librarian finds a book where the key on the spine perfectly matches your query card, they hand you the actual pages. That's the value vector. It's the actual underlying information or context that gets handed over when a key successfully aligns with a query.
Mechanically speaking, this whole library system is just built on matrix multiplication. Every single word takes its initial embedding and multiplies it by 3 distinct learned weight matrices. And boom, that simultaneous math produces a unique query, key, and value vector for absolutely every word in the sentence.
Moving on to section 3, the math. Scoring keys inside the scale dot product engine.
Okay, let's look inside the actual computational engine. There are 4 systematic steps that control how all these vectors interact. Step 1, the dot product, which gives us a score. Step 2, we scale that score to stabilize it. Step 3, we apply a softmax function to get probabilities. And step 4, we do a weighted sum for our final output.
So step 1 relies on the dot product. If you remember your linear algebra, this is just a way to test vector alignment. The system takes the query vector for the word it and calculates the dot product against the key vectors for both trophy and suitcase. This raw score is just measuring semantic similarity. Because the vectors for it and trophy point in a similar direction in this massive high-dimensional space, they get a really high score. Meanwhile, suitcase gets a much lower score. Then, in step 2, we take that raw score and scale it down. We do this by dividing it by the square root of the key vector's dimension. You might be wondering, why bother? Well, without this stabilizer, the dot product variance just gets way too large, and that would push the math later on into regions where training literally stops working. So this scaling factor is absolutely crucial to keep the whole process stable.
Next up, section 4, scaling and softmax probabilities, converting raw scores into attention weights.
All right, step 3 is where we apply the softmax function. This is super cool because it forces all of those raw scaled scores into a normalized probability distribution that adds up exactly to 100%. So instead of arbitrary math scores, we now have a strict attention budget. As you can see, trophy completely wins out, capturing exactly 80% of the attention. Suitcase gets 15%, and the rest of the words in the sentence just get the remaining 5% scraps. And for our final step, step 4, the model takes the value vectors, multiplies them by these brand new attention percentages, and sums them all up into a single context-rich representation. Because of this exact math, the word it is mathematically infused with 80% of the essence of trophy, completely updating what it actually means in this specific context. Finally, section 5, multi-head attention perspectives, seeing all angles at once. Here's the crazy part. Modern AI doesn't just do this calculation once. It actually runs this exact scaled dot product math in parallel, using multiple heads where each head has its own independent set of learned weights. So one head might be completely focused on figuring out grammar rules. Another is tracking the semantic meaning. A third might be tracking long-range references. All these parallel mathematical perspectives are calculated at the exact same time and then combined, giving the AI an incredibly robust multi-angled understanding of the text. So at the end of the day, there's absolutely no magic here. It's literally just queries checking keys, scores turning into normalized weights, and every single word quietly voting on what matters mathematically. But, this leaves us with a truly mind-bending question. If this beautiful, elegant vector math is just a single block of attention, what kind of unbelievable emergent reasoning starts happening when we stack hundreds of these blocks together to build a full transformer architecture? Something to think about as you continue your learning journey. Thanks so much for joining me for this explainer. I'll catch you next time.